Oh, oh, I see. Okay. Okay. So clearly, this is a tough crowd because the last time I gave a talk on HHL, the audience halved in the next session. Glad to see a lot of people are sticking around. And you guys are in for a treat because this session is going to be on far more manageable topics.
Sorry.
I mean, hello? Yeah, it can start like, but so before continuing with the next part of the talk, I would just to like to mention a few of the resources that you can use if you are interested in these kind of algorithms. So there is this brilliant 300-page survey. Where are the chalks? Chalks. Is there a big? This is a chalk packet, right? Yeah, yeah. So there is a brilliant 300-page survey by Andras Gillian and like some 10 to 11 co-authors. I think like there's another guy called Fernando Brandao in there. So they came up with this 300 page. I won't call it a survey. It's a survey. It's more like a wiki of the current state of the art in quantum algorithms. And almost all of them work at Amazon Research, like some research lab associated with Amazon, and they're affiliated to their own institutes. You can just Google like this came. You can go to Andrash's Google Scholar and look at things that came out in 2023 and just go for a quantum algorithms, a survey of quantum, something like that. So I forget. Can you just check like what the title of the thing is? Yeah. So the reason is that I'll give you a small example. So right now we are going to be discussing something called block encodings and something called LCUs. These tie into what is known as like the Hamiltonian simulation framework. For those of you who like got the crux of the last lecture was that these Hamiltonian simulation frameworks allow us to design and analyze quantum algorithms in a easier fashion. Sometimes it's even robust compared to like what we used to do prior to these frameworks. This can be generalized to the quantum signal processing framework, which is what like I'll give you a brief introduction in words is given any operator, any Hamiltonian, let's say, operator will come to later on. Given any Hamiltonian, you can encode that as a Szegedy walk operator. So you have been attending Sham's talks. So Sham is talking about quantum walk algorithms, right? I don't know, like I have not seen his lectures, but has he talked about like solving problems as quantum works? Has he gotten to that point yet? So maybe by the end of today, you will see that because let's consider Grover's problem for an example, right? You can approach Grover's from multiple viewpoints. You can view it as a standalone algorithm. You can think of Grover's as this Hamiltonian simulation algorithm that simulates this walk operator over and over again. You can also think of Grover's as a quantum walk operation. So, given any general quantum circuit, you can sort of think of it in this Szegedy walk framework, which again, like Sham will cover at least some part of it. Maybe like if I have time later on next month or some, I can also discuss QSP and QSBT. Like, but the point is that you can generalize quantum algorithms and try thinking of them in these bigger frameworks. So this quantum signal processing framework is also encompassed by what we call quantum SVT algorithms, the quantum singular value transformation framework. In fact, Andras Gillian is one of the researchers who gave this framework, and you will find a lot of these like excellent papers on there's a very excellent paper named A Grand Unification of Quantum Algorithms that introduces that does not introduce this, but it takes the QSBT framework and explains how any given quantum circuit can be encoded into this particular framework. Now, even though I'm not introducing these things, the reason for pointing all of this out is because this is a bootcamp designed to teach you quantum. If you want to start thinking about quantum algorithms, you can also start thinking in terms of frameworks. That's the main point. So, in theoretical CS, in any field or subfield, we have these big hammers, right? And you can use those hammers to attack any problem. For example, randomized algorithms has a lot of hammers. Approximation algorithms has a lot of hammers, right? So these are some of the hammers of quantum computing. So this is just the setup. Now I have a question for the class. Let's say the task. And because I said we are going back to basics, I want you guys to think about these. Task number one. Given unitary U, apply the map some V. Throughout this lecture, this will refer to states that we don't care about. So we can just use like some sort of amplification to get rid of those states. So this is task number one that we'll be tackling today. Given a unitary, I want to apply this unitary probabilistically. This is the first point. So you can think of this as square root p. Is everyone clear on the question? Let's say I want a unitary that does Hadamard transform, right? But I want the Hadamard transform to take place. I think I should stay over here. If I want the Hadamard transform to take place, I want the Hadamard transform to take place with some probability. I don't want the map to be implemented directly. This is task number one. Task number two. Given 1 second, I'm just getting back to you. So given two unitaries u and v, we want to apply the sum of these unitaries to the operator. Yeah, what was your question? I don't know what the other 1 minus p is. So this state is basically some root 1 minus p in and some state, right? Because I'm not applying u, I'm applying some other unitary, u dagger, right? U dagger, nahi, u tilde, let's say. So I don't care about this state. So this is what I. So okay, again, if you are not familiar with the notation in quantum papers, we usually mean that this state is still normalized. It's just that we don't really care about the normalization in this state. So given this part, this is the only part that I'm focused on. This state takes care of your normalization constants. So this just means that, yeah, I should have been a little, because I keep forgetting that like this is a boot camp. Yeah, yeah. So I mean, so any that orthogonal state basically takes care of your normalization problem, because this root pu may not be a normalized state, right? It's not, it does not have amplitude like probability one. So that state takes care of that normalization problem. So these two tasks, right? Which task like seems more intuitive, which seems less intuitive? Can you just say? And we have a lot of time. We can like the second task is given. Should I write it? Yeah, I think I should write it a little better. So given two unitaries u and v, apply u plus v to psi, where psi is any arbitrary quantum state. So can anyone identify the first problem with the second task? We'll come to the first task in a bit. Very good. U plus v may not even be a unitary. Can you give me an example of a u plus v which is not a unitary? Very simple example. Minus identity. Identity plus minus identity. Minus identity is a unitary. Identity is a unitary. It will, the resulting thing is just a zero matrix, right? So u plus v may not even be a unitary. It might be like non. It might be singular operation. These two tasks, and this is also not a trivial task, by the way, because it would have been a trivial task if psi was known. But now I'm asking you to apply this to any arbitrary psi. Can someone tell me why this would be a trivial task if psi was known? I want to develop your intuition for these sort of algorithms. So let's say if I tell you that psi is the plus state, can you tell me like given any unitary if we can apply this? Very good. If you know the state, if you know the unitary, you can design a hard-coded version of V. A better way to think about this, a more sophisticated way to think about this is, if I know what psi is, I can do sort of a conditional rotation on psi and then just apply the U. So I can just do a conditional rotation on psi with root p psi and something else and then apply U, and the resulting state is root p u psi plus whatever I don't care about, right? So here now the problem comes. So all of these quantum advantage stuff that people talk about is usually done on things that we don't know. It's done on arbitrary states. So given an arbitrary state, you can immediately see that this becomes a non-trivial problem. This applying this root p u psi. So is anyone like not convinced that these are not trivial tasks, right? Now, in order to develop your intuition about designing frameworks for algorithms, can you tell me that if I have access to these two sort of operations given to me, how can I improve HHL? Forget HHL. How can I, like, what is the power that these two operations give me? You are moving into this classical territory, right? Like classical application of classical. So you are very close. So, in fact, if I have these sort of algorithms that do these kind of tasks, I can go for these quantum inspired classical algorithms. Okay. And in fact, there is a paper by Even Tang and authors. Again, I'm very bad with names. So, like, I don't know. And the problem is in HHL literature, every paper has almost the same name: quantum linear systems primer, quantum linear system algorithm, these kind of names. So there is this paper by Even Tang who gave a quantum inspired. So she looked at the HHL algorithm, she and her co-authors looked at the HHL algorithm and came up with a better classical algorithm for the task. So we saw the conjugate gradient method in the beginning, right? So their algorithm actually had a better complexity. And that was achieved by looking at the HHL algorithm and designing classical algorithms that were very similar. And they solve the LSP task, not the QLSP task. There's a distinction to be made. So this actually helps us with this particular, even though it might not be straight away relevant for quantum, but this This framework actually allows us to do something even more general, which might seem surprising at first. If I know how to do task 1 in full generality, so given any shy and any unitary, if I can do that sort of a task, I can also do this task. Take a moment and think about this, what I'm talking about. Given any linear operator, it does not even have to be square. Any linear operator, we can do this particular map. Let that sink in. From the first day, you have been told that quantum operations have to be unitary. It's not exactly false, but can you imagine like what power we have in our hands if this was possible? Yes, exactly. Yeah. Again, algorithmic thinking. So mathematically speaking, whenever we have a unitary, right? A unitary acting on a qubit is basically a well-behaved linear transformation of on some Hilbert space, right? So any unitary, this was covered in the basics, right? I don't need to go too much into the basics. So any quantum state is just a normalized vector on some Hilbert or complex valued Hilbert space, right? Now, in the next boot camp, you will see quantum information coming up. So there we will actually talk about this idea of why doing this is even possible. Like you can take two quantum states and then like combine them like classical registers. So we know that this is a tensor operation and mathematically it works out, right? But why does this even make sense is not something that's explored in quantum computing. So you can have two classical registers, psi and a, and instead of that, you can even encode them into two separate quantum states, psi and a. And if a is like say m qubit and psi is n qubit, then we are basically working on this 2 to the power n plus m dimension Hilbert space. Everyone like agreed with this? Okay. Here is where the trick comes. Let's say I have a generic linear operator that I want to perform. The trick that I have to identify is this generic linear operator can be thought of as acting on a subspace of a much larger Hilbert space, which a unitary can act on. So, if unitary U acts on this Hilbert space, we can always think that this linear operator A acts on this Hilbert space. Because we are applying this particular unitary, we can get away with this. So the quantum operation will still be this particular unitary that we are applying. But if we measure and restrict our search to this particular Hilbert space, so you have already seen algorithms like this, Joyce Joza. Yes, very good. You have a great student here. So Joyce Joza algorithm, right? What does Joyce, the Deutsches problem is fine. The Joyce Joza algorithm is a promise problem, right? If you measure 0 in the first register, then 0 or 1, I don't know what notation he used, then whatever you get like is a correct answer, it's a balanced answer, right? So that means I don't care about what goes on in the other part of the Hilbert space, I just care about what happens in this part of the Hilbert space, right? So we have already seen algorithms that take this particular structure into mind. So when unlike classical, like classical we can just read some of the input and discard the rest as garbage. Quantumly also we are trying to do sort of the same thing. We're just reading one part of the input and discarding rest of the garbage. Fine. Any questions up to this part? Yeah, yeah. I mean, this part actually will be covered by the quantum information theorists. I actually have very limited knowledge of that part, but there is like, if you guys are look, huh? Yeah, I mean those are super operators. So good. Okay, again, I don't want to like make the job for those guys easier. Let them do their part. But there is a fun concept called the church of the larger Hilbert space. Like, is anyone aware of this? Yeah. So physicist, obviously, you will be aware of this. So the idea is that okay, you treat these quantum gates as channels, right? And you're passing something through the channel. So think about normal communication, right? So if you're passing some message through a channel, if the channel acts like an operator, it will change the message somewhat, right? So if you combine multiple channels together, it it the message on the other end will be exactly what the channel dictates the message to be, right? Quantum circuits are also similar to that, and I'm simplifying this in a large way. So essentially what it is saying that you can sort of combine the action on all of these Hilbert spaces and construct a larger Hilbert space, and everything works out perfectly. So this is like the church of the larger Hilbert space concept that people think about. And the thing that oh, I don't know your name, huh? Anupam. So what Anupam was talking about was this Choi representation. There are things called cross representations. So what you do is when you have an operation on a Hilbert space, and if you want to bring it up to a larger Hilbert space, instead of that operator, you construct a super operator of this particular thing. So there are super operator representations. Again, like this is a separate, it goes into operator theory and much more. But for the sake of quantum information, there are these very nice forms called Choi representations, like Choi Jamolsky representation, I think. Yeah, I forget the second guy's name. My bad. Yeah, Choi Jamolsky representation, cross representation, and many things that go on. If I have the chance to talk about quantum learning algorithms, maybe in some like future boot camp, we will see that this concept actually comes into play later on. So, but we'll leave it for the time being. We want to tackle these elementary problems for the time being. Okay, very good. Yeah, yes, yes, very good. So we want to stay in the good subspace. Exactly. So now the thing is, given A, we want to embed A into a block of a larger unitary UA, like, so we want to do this operation. How exactly does this help us? Let's say this is acting on some, yeah, but I don't want to go because cubitization is a little bit different from this. This is much more general than cubitization. Cubitization again leads into this QSP sort of framework. Yeah, but it's cubitization was born out of this idea. Yeah. For those of you who don't know cubitization are, forget it. We don't need it. So let's say I want to apply this on this particular state, and let's say that A is an S qubit operator and psi is an S qubit state. Okay. So what we get is essentially again A psi plus something else that we don't want. Agreed? There is an obvious problem with this setup. Can someone spot it? Can we do this for any operator A? I'll give you a hint. The problem lies that we are encoding this particular operator into a unitary. Hmm? No, so the blank parts take care of that. That's not what I'm talking about. There is a much more subtle point over here, which is not so subtle actually when it comes to the problem. To help you, the answer is partially given in task 1. So think about this. I'll ask another question. What are the eigenvalues of a unitary matrix? Roots of unity, right? If I have a generic linear operator, right, when will this construction become invalid? And this is a math question now. I heard an if. But this is fine. You can like you were learning this for the first time. Tell me. I care about whether U is always diagonalizable, right? The problem is consider when the spectral norm of A is greater than 1. Can I ever encode it to this unitary? Then I cannot. Right? Everyone clear on why we cannot? Okay. But there is an easy fix for this, right? Again, task 1. So I'll keep on relating. So let's say, yeah, very good. Some you can normalize. So let's say the spectral norm of A is at most some alpha. I can just divide this by alpha and get something like 1 over alpha over here. And this we can do. Which straight away tells you that if you have an unitary U and you want to do that particular task, all you need to do is you need to construct a larger unitary with that square root with a now instead of A, if you have a U, just apply square root P over here. And you can immediately do task 1. So the idea actually was built because of that task. This is fine, right? Okay. So for a moment, going back to A over alpha. Now see, if A is an S qubit unitary, UA is not an S qubit unitary. A is an S qubit operator, it's not a unitary. Let's say U takes, so if this acts on S, this acts on A, let's say. So if UA takes A ancilla qubits and uses the normalization factor alpha and implements this with error epsilon, which I will get to what error epsilon means, then UA is called an alpha A epsilon block encoding. So UA is of A. The reason I'm not defined epsilon is because there is a little bit more technicality required to define epsilon. But you can think of it like this, just in the Hamiltonian simulation case, there will be some error when we are doing these sort of things, right? Because we are implementing it probabilistically. The A, 1 over alpha factor comes in. Because of precision and other stuff, I might not be able to apply A psi directly. There is some error that comes in. The error term I will precisely define what error means over here. But everyone is comfortable with this sort of a setup? Any doubts with the definition of alpha A epsilon? Okay. So UA is an alpha A epsilon encoding of A if this condition is fulfilled. Just because I wrote a huge equation on board does not mean anything. This is actually a very simple thing once we get down to it. A small task for you guys, because we have a lot of time for this session. Can you follow along and try and understand why, what is happening with this part? Can you try to do the computation on your own copy? Try to see what this operator comes out to be. Do it on your own copies, because like it's a little hard to parse the first time you see it. So I'll give you another task. Let's say, so yeah, A is the ancilla. Whatever extra qubits UA is using, A is not that. Yeah. What is the value of this observable? This will make the task a lot easier to think about. The ijth entry. So that observable basically gives me the ijth entry. Now, if I do a summation over those, I basically what I do is I isolate a block out of the matrix A. That is precisely what is happening with these operators. I am isolating a block. So I think this should be S. Yeah, my bad. Yeah. I am isolating an S cross S thing out of the larger unitary. In fact, it would do us good to look at the full explanation once. So let's say I want to apply this particular operator on some S qubit unitary psi, right? Let's do it step by step. I'm no longer writing the 0s because it's becoming too tedious now. Fill the dimensions in yourself, but verify that this is correct. So this is nothing but a 1 followed by zeros. And when I do a tensor, so I psi is just psi comes inside. So I'm doing a 0 tensor with psi, right? So 0 tensor with psi is 1 tensor with psi, then 0 tensor with psi all the way through. So effectively, I end up getting an S plus A state where this is S and this is, oh, this is A. This is A. Yes, I was correct. No, no, no. This is like this notation is a little like wonky. I'll show that this is fine. Yeah. So this is A. This is fine. Yeah, yeah, yeah. Yeah. This notation, like even I get confused like sometimes. Yeah. So this is an S plus A quantum state, right? Because everyone familiar with tensor products, how they work, right? This is the state. Now I'm applying UA, which is an S plus A unitary, onto this particular state. What do I get? UA is defined above, as above. Yeah, so like, can you tell? So, okay, yeah. So you get 1 over alpha A psi plus C psi, right? This is the thing that I end up getting. Now look at this. 0 tensor I. This is nothing but the operator I0. I0 applied on this state, I just get 1 by alpha A psi. Fine. Then I multiply with alpha. And what is left? Just A psi. So this operator, this alpha into this projector U this, is nothing but some, okay, this calculation is fine, right? I'm just rubbing the calculation. I just wanted to go through the notation once. I'll rub it. Okay, I'll write it here. So this A minus 0 tensor I UA 0 tensor I is nothing but A minus some A tilde, and I want the operator norm of to be less than epsilon. This is exactly what's going on. Now the first question that might come to your mind is, okay, this might be 0, right? If A is directly encoded. But again, like as we have seen before, it might be hard to even get A directly in. So we are assuming that this operator is something which is close to A, which yields something close to A. So the operator norm between these two is at most bounded by this epsilon. And again, another interpretation is you take the larger unitary and you isolate a block out of the unitary. And that block has to be exactly equal to the linear operator. Now this calculation that I did and this notation that I wrote works for any square matrix. Invertible, non-invertible, Hermitian, non-Hermitian, anything. For general matrices, like things that are not even square, you just have to pad them with zeros to make them square. That's it. Nothing else. This is a very general form that we have. Any questions with the block A? So it's known as an alpha A epsilon block encoding. So now when we look at specific problems, we will see A comes out of the problem. So if I know the S, it might not be. For example, I'll tell you. So if A is a particularly difficult Hamiltonian to simulate, then the number of ancillas might change, even if I know what the S is. So it depends from problem to problem. So the even though we have the framework, the joy of designing good algorithms is still not gone. So the specifics are still left for us to figure out. Yes. Yeah, that is what I that is what I was saying. So you might think that A tilde is nothing but A. So it's just 0. But as we will see later, that it might not always be the case that UA encodes A over alpha exactly. It might encode something that is close to A over alpha. We can say, but we wanted to keep it like more general. So we can say that, of course, we can say that this is that's a good point that he raised. So in fact, if UA is A tilde over alpha, it's still a block encoding alpha. In good point. So if I just have such that A minus A is less than epsilon, then this is a alpha A epsilon block encoding of A. Even in that case, is there something going on with the mic? Is it me or is it? Oh, acha, acha, it's not because of me. Okay, fine. So yeah, good point. Fine. You figured that out as homework. No, I mean like you can figure out the dimension of the identity directly, right? Yeah, yeah. So the dimension. So I is an S cross S identity. No, no. So yeah, yeah. I mean this is an S qubit identity. So this will be 2 to the power S cross 2 to the power S. How do we figure this out directly? In the last step, this is just isolating out the this part, this subspace, right? This subspace is an S qubit subspace or 2 to the power S cross 2 to the power S. So you can do the calculation, but one day to leave something for you guys to do. Yeah. Okay. So now I have questions for everyone. Yeah. Yeah. They act on the same subspace. Dimension, yes. A tilde is also, it is UA is in S plus A. A tilde is again back in S because we are we are just projecting out that subspace. Yeah. True. So question. Given unitary U, prove that U is a 100 block encoding of U. Easy problem. Given a unitary U, show that U is a 100 block encoding of U. So alpha is 1 because U is unitary. It does not use any extra ancillas to encode it. U minus U is 0, right? So the error term is 0. So it's a 100. Okay. Before giving the second question, I want to point something out. This is what is known as a signaling state. This 0. You can in fact choose to encode the unitary anywhere in the bigger unitary. It does not need to be on the left subspace, right? You can put it in the middle, put it to the right hand side, put it back. Depending on where you encode it, the signaling state will change because this basically identifies the top half of that block. We have already seen that this ij, the observable ij, right? So if I change it to some other I and j, that block of the larger unitary encodes a matrix. Where will this become useful? Prove that controlled unitary is a 110 block encoding of U. So let's do a small example. X gate is what? Tell me the X entries, someone. 0, 1, minus 1, right? So, right? And the control X gate can be written as, we'll do it the sophisticated way now. Yeah. No, no, this is 1, 1, 1. Sorry, this with phase, I confused it with phase. Yeah, right? And that is the controlled unitary, right? So given any unitary U, the controlled unitary will be either the indicator state into the unitary, a tensor with a unitary. Which one? This one. This is the outer product, 1 cross 1. Sorry, sorry. I have a bad way of. No, no, no. Yeah. I mean, these are bad habits you pick up from LaTeX because if you write the bracket notation, it just comes 1 cross 1. So, yeah. But any control unitary can be written like this, right? So, can you now show that the control unitary is a 110 block encoding of the unitary? What is alpha? Alpha is just 1, right? Because unitary is, it has eigenvalue roots of unity. Yeah. Number of ancillas? Just 1. Error is nothing because we are just implementing the thing itself. This tells you, now see, we just took the generalization, a definition and generalized it. Control unitary no longer has the encoding in the top left corner, right? You have it somewhere below because this 1 cross 1 is dictating where the thing will go. So Immediately we took a definition and generalized it. Next thing, now you can you think of Hamiltonian simulation or phase estimation in the block encoding way? What is Hamiltonian simulation? Is the phase estimation thing. You have a sum over this J cross J things tensored with the Hamiltonian that we are trying to apply. So let me just write that on board so that it's a little bit more obvious. So in phase estimation, what do we do? Sorry. This is the unitary that we keep on applying again and again, right? So that means we are just applying a block encoding of the unitary U over and over again in superposition. Immediately we see that this Hamiltonian, this phase estimation thing can now be termed as a block encoding framework. So uh, phase estimation is just, so you just have 1 to n. So you can 0 to n minus 1, whatever works for you. So this is just a bunch of controlled unitaries that we are applying, right? Immediately you can see that block Hamiltonian simulation can be formulated as a block encoding. Hamiltonian controlled Hamiltonian simulations are exactly this. So the first step of HHL can now be written, and take this as a homework. Try to write the block encoding of the HHL algorithm. What happens? It's a very interesting exercise. Okay, try to figure out what A is and epsilon is. That's the fun part. Yeah, it will be one. The because you are encoding a unitary, the normalization will be one, but alpha and epsilon are the interesting things to figure out. So take this as an exercise. Okay, wait. I have lots more of fun exercises. My bad. Ah, let me write this as 1, 2, 3. Hmm. Yeah, I'll come to so okay. One of the most general motivations is given any linear operator, now you can do the transformation. This was this obvious when we were learning about quantum computing. This was not obvious, right? So that's a huge motivation for block encoding. And thank you for the question. So as you see, we immediately went from just defining a general construct to start putting already known algorithms into this particular framework. So the motivation behind everything that we will study in in the next 1 hour or 1.5 hours is we want to go towards this grand unified theory of quantum algorithms. So in fact, like whatever Sham will be doing, the quantum walk framework, as I was saying, it can be sort of put into this qubitization and quantum signal processing framework, which themselves are just generalizations of block encoding. So even in quantum walk, right? What do you do in quantum walks? You see where you are, and then you do a transition based on where you are. That's what is going on. So you are basically applying a conditional unitary, or you are not applying a conditional unitary, which is exactly what we are trying to do over here. That's just a walk operation. And the way to implement that is by block encodings. Like always keep the bigger picture in mind. Very good. I'll come to that. But that's actually, I'll come to that. This should be immediately apparent, right? If u is an epsilon approximation of, if u, sorry, u tilde is an epsilon approximation of the unitary u with a ancilla qubits, then u tilde is nothing but a 1a epsilon block encoding of u. Now the question is, this seems trivial, right? From whatever we have seen before. Why would you, given a unitary, why would you even go for an epsilon approximation of this unitary? There are two motivations. One is a theoretical motivation. The second is a hardware motivation. You guys are familiar with Qiskit? Chetan, like you did Qiskit, right? So in Qiskit, what happens is when you implement unitaries, now, so you can go down to as much depth as you want. One of the things that you do is you transpile the unitaries into these generalized rotation gates, u, theta, gamma, phi. So any unitary, because unitary operations are just rotations, any unitary can be decomposed into a rotation on a block sphere, on a generalized block sphere, right? But now a block sphere is a complex valued entity. We have finite precision on our computers. We can't exactly approximate every possible gate, right? Because pi cannot be exactly represented. So even for unitaries that you think you know, you can't have exact representations on the computer, right? So therefore, even given a unitary, you would get an epsilon approximation of the unitary on a hardware level. In fact, it gets much worse when you actually go down to how quantum computers actually work. They work by shooting these microwave pulses at electrons, which is for physicists like Rabi oscillations. It's even worse at the hardware level. So even if you think you have a unitary, you don't have a unitary, you have an approximation of the unitary. This point becomes important there. Second point, again going back to Hamiltonian simulation, maybe the exact unitary takes you infinite time to actually simulate. But if you do the Taylor expansion and chop off the cubic terms and more, you immediately have an epsilon approximation of the desired unitary. This point comes into play over there. Hopefully, like this motivation is clear. As Abhirup, right? On Anupam, sorry, my bad. Yeah, you can see that my statement was true. Okay. Do you guys know what density matrices are? So density matrices are just classical ensembles of unitaries or quantum states, let's say. Should I rub this? Yeah, I mean, you have copied this down, right? Yeah, I can't keep this forever anyway. If you have a density matrix rho, which is nothing but summation of I classical pi into these rho I states, I can immediately try to construct a unitary that applies the density matrix directly onto something. This much should be clear by now. The exact ancilla and the exact error of this operation is actually a little difficult to figure out. Like it detracts from the main message because then you would have to know the Schmidt rank of the operator itself, what we are talking about. So I just wanted, you can read up on this on your own. I will provide like notes to this. We can apply these. We can also apply POVMs. Because POVMs are of this form themselves, right? So we can just apply POVMs as block encoded unitaries. So the next time somebody tells you that you have a quantum algorithm and you need a measurement and you need to go forward. So There's this nice thing that I don't know if this was covered or not. If you have any measurements in the middle of a quantum circuit, you can always defer it to the end. Deferred measurements, right? This is another way of looking at deferred measurements. Because everything can be put into a larger Hilbert space, you can consider everything as a unitary encoding. And since it's a diagonal unitary, this will form a diagonal unitary, you can push it towards the end. So you can see this, like if you work out the details, you will see this. But again, these things tie in back together. So you can implement density matrices, you can implement POVMs. But we would like to do something a little bit more exciting. Let's say I seem to have problem writing 5 today. I'm constantly writing 2 instead of 5. So let's say U is an alpha A delta encoding of A, and V is a beta B delta encoding of B. Let's say we have this setup, right? Prove that UV is a I've left those intentionally blank for you guys to figure out. So now we are using block encodings as building blocks. Given the block encodings of two different unitaries, let's consider them as unitary. These are matrices, general matrices. I'm telling you that multiplying the block encodings of these matrices would give you a block encoding of the multiplied matrices. I mean, it seems quite reasonable, right? Actually, this this is the operator. This operator is a block encoding of that. Can you take 2 minutes and try to figure out the first steps? Now, what I want you to figure out is how to go about proving this. So the idea why I want you to figure out the first steps to proving this is, let's say you have a complicated operation in the future that you need to perform, right? So you design block encodings, but if your block, like how do you even prove that you have gotten a block encoding or a good block encoding? So can you try to write the first steps of proving this? Just the first step would be enough. A tilde B, A tilde B tilde is bounded by some epsilon. Right? Yeah, yeah. You don't need to apply it on vector. You can just check the operator norm. Yeah, 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 yeah. So number of ancillas would be A plus B. Yeah, A plus B. Mm. So number of ancillas is A plus B. We have a first answer. What is the scaling factor? Yeah. No, scaling factor is like we don't consider that as 1 by. We divide by the scaling factor is alpha beta. The ancillas are A plus B. Correct? What is the error? Can someone try to hazard a guess at the error? Sorry, let's make this epsilon. It's not a very intuitive guess, but it's something a little bit more. So in fact, the guess you can sort of get from this. Yeah, no, alpha. Yeah. So the error term is actually alpha beta a plus b, and the error term is alpha epsilon plus beta delta. Do you guys want me to prove this, or can you do this yourselves? Because I have given you the operator also. It's just expressing the entire thing out, getting this AB minus A tilde B tilde. So the first step is showing that 0 A plus S tensor I and this, the conjugate of this on the other side, just gives you A tilde B tilde. This is the first step. And alpha beta into this. This is the first step. I'm giving you the proof sketch, showing that this is alpha A tilde B tilde, which is pretty straightforward. You just have to take care of the tensors in here. Next thing you show that now I am working with trying to find the error of this. What you do is you break this into AB minus, now you apply triangle inequality, Cauchy-Schwarz, anything you want, you will get the expression. So the idea, so there is one more small crucial step is, if the spectral norm of A is alpha, at most alpha, then the spectral norm of A tilde will also be at most alpha, because we are already normalizing it, right? Similarly, it goes for the spectral norm of B. If it is almost alpha, almost beta, the spectral norm of B tilde is also almost um, beta, because we are normalizing it. Again, we can take the things common. We can apply a larger inequality out front. Here you can take B common, so you get a beta. So you get a beta term, and A minus A epsilon is just delta. So you get a beta delta already. Do the opposite over here, you get epsilon, alpha epsilon. Try to do the entire thing on your own. This will make you more comfortable with working with the tensor notation. Right? Okay. Because we are all about building stuff from smaller to larger things. Given this, can I expect you to, yeah, yeah, please. Just interrupt me if you want. Yeah. No, no, no. Alpha and beta can be anything. You are using that to scale the norm of the matrix down. Okay, so like because we are working with general linear operators, alpha can be larger than 1. We don't care. In fact, if it's less than 1, it's already subnormalized, so we can construct a unitary out of it. So we don't really care about that. Okay, any other questions? You can do start with the spectral norm sometimes. In fact, I'll do you one better. If A is not diagonalizable, alpha is just the Frobenius norm of the matrix. So the largest value in the matrix, you can just take it as that. In fact, I'll do you even one more one better. So in order to get better scalings, instead of the Frobenius norm, we go for these LP norms of the matrices. So like you can now you if you know the framework, you can play around with it. We don't really care about what alpha is, but we just have fun with it. That's the entire point. But yeah, now that we have this, okay, one small thing I'll mention over here. So triple IT does not have blackboards, which is a huge pet peeve of mine. I like blackboards. So six. This is six, right? No, this is seven. So let's say U is an 1A epsilon encoding of unitary A, and V is a 1A, same number of ancillas, yeah. Delta encoding of unitary B. Okay. If we do it in a normal manner, you will see that we require A plus B number of ancilla. But if both of the things that we are trying to block in code now are unitaries, we can actually get away by showing that again, similarly, this I tensor U and IB tensor V, whatever. So both of them will be the same thing now. You can actually end up showing that this I tensor U into I tensor V is a 1A 2 epsilon plus delta plus 2 square root of epsilon delta block encoding. The number of ancillas now reduces. You don't need 2A ancillas, you need A ancillas. But in order to do with 2A ancillas, you have to pay a little bit in the error. Now, can someone tell me, because we are now again all about frameworks, if this is a good trade-off or not? Because see, keep in mind, we can keep to the previous trade-off and get 2A, right? And we can get an epsilon plus delta. So we can have this 1, 2A epsilon plus delta error just by using that sort of a approach. Now I'm telling you that there is a way to reduce the number of ancillas with paying a little bit extra error. Can someone tell me if this is a good trade-off or not? Why? Ancilla qubits? Yep, yep. So does everyone agree with this that oh, I see. Oh, feedback. This is the golden spot. Yeah. So does everyone agree that the lesser the number of ancilla qubits, the better it is? What are your reasons? Huh? Yeah. I mean, yeah. So I can ask you for a theoretical reason. It's not just this. Space complexity. Exactly. So there's both a theoretical reason and an implementation reason. Of course, like if you're working with quantum computers, I personally don't care about what the hardware limitations are because the kind of algorithms that we work on, it's as noisy as this. So yeah, I mean, but theoretically also there is a very good reason to keep the number of ancillas down, even if you have to pay a little bit of error, because at the end of the day, this is not too much error. It's just paying a linear term in epsilon or delta more. That's it. Okay. So now, should I rub this or should I rub that? No, let's keep the tasks up. Okay. 8. So given uj is equal to 1. Hmm. So this is a pretty powerful result now. We are just going from multiplying two unitaries or two matrices to a product of k matrices. And the great part about this is the number of ancillas doesn't increase. Of course, we are paying for it in error, but it doesn't really matter because if you consider like you're multiplying a constant number of such block encodings, it's still linear in epsilon. Why is this a fascinating thing? Let's say I want to apply UV on some state psi, right? I can simply apply them one after another. So the circuit would sort of look like I have psi, I apply a V, then I apply a U, and I have UV, right? Now what I'm telling you is given any like k linear operators, you can do this exact same thing with just a ancilla qubits more. Just imagine like the power we are getting now, and you are just paying some linear like error more. Like, hopefully, like this should be like the more you think about it, the more impressive it becomes actually. One point to notice, all of these algorithms, like all of these results are proved in Gillian's another one of Gillian's papers about quantum singular value transformation. So in the paper that he actually introduces the QSVT framework, he actually builds up these block encoding results first. So all of these results and their proofs are actually even the POVM and the density matrices. So there is a paper on Hamiltonian simulation. I will be providing all of these references in my notes so you can check them out. But here is another great researcher you should follow. So Apple, I am pretty sure I butchered his name. It's Apple Doon. So Van Appeldoorn, the Jordan Van Appeldoorn, like he is also a very young researcher. Like he just entered his postdoc a year ago. His papers and Andras Gillian's papers, both of whom are like barely in their 30s, like mid 30s. These people sort of gave this incredible framework for Hamiltonian simulations. Like you can take a look at both of their theses, and you will find that like all of these results are covered in detail. Andras Gillian and Jordan Van Appeldoorn. If you search some combination of Appeldoorn, you will get Appeldoorn, Doorn, Appeldoorn. So all of these results, like there are concrete like places where these have been proved. Okay? So tasks number 1 and 3 we have seen very like in too much detail at this point. What about task number 2? Because we have seen so many tasks, can you take a moment and think about task number 2? Huh? But multiplication will not give you the sum. So you on top and so dimensions are same. Let's say both of them act on s qubits. Yeah, V on the bottom left, right? So I think you are referring to something like this. Which one should I rub? This one? So I think what you are referring to is where I have a larger matrix where U is encoded here and V is encoded here. Yeah. I mean, this also works, right? Yeah. But like this would require that you have two copies of Shai, right? Something like this. I mean, you would need it to be this sort of an encoding, right? Which is very good. Like, in fact, I hadn't thought of that solution before. This works. What is the only problem with the solution? There is one thing extra that we need in this solution that we were not assuming anywhere else. So let's go over that's very good. Like let's go over the assumption one by one. We can do a block encoding of U in the top left corner, yes. We can do a block encoding of V in the top left, bottom left corner. Yes, we have already seen this, right? This is not a problem clearly. So the problem clearly lies in this part. What is the problem? Exactly. So was Holevos bound and everything done in like again quantum information. So but no cloning theorem, I think like that everyone knows, right? So if I tell you that if I have an arbitrary quantum state, you can't construct this quantum state. I mean, it's not trivial. You would need multiple. So, for example, I'll again bring it back. This is a very ingenious solution. If you put V over here, no, I mean anywhere you put like you would like still need, yeah. So it's a very ingenious solution by the way, because if we saw that TB actually maps 0 to B, right? So now I would just need require two calls to TB to construct this state. You can construct this state, right? The problem is something that I did not mention. So it might seem like a reasonable thing, but the problem is something that I did not mention when I was talking about HHL, which we were discussing during the break. This actually assumes a QRAM setup, this TB thing. And if you don't know what QRAMs are, fine, we don't need them. They are just very frowned upon objects in theoretical CS because QRAM sort of give you this magical power to do random access queries on quantum objects. It's not desirable. In fact, having one query to QRAM is bad enough. Having two queries to QRAM is extremely bad. So most of the algorithms, like if I get to talk about quantum learning algorithms, most of the algorithms just use the QRAM access once, and that too also to prepare uniform superpositions. Nothing else. Having two access to QRAMs is extremely like undesirable. But this is like great solution that you gave, and of course, like this sort of solution works. But can we do something better? In fact, try this out. L- huh? Yeah. I am telling you that u plus v, u and v are unitaries. U plus v can be anything. Yes. Now. Yes. Yes. Very good. I can just encode u plus v in block encoding, right? This is the answer I was actually looking for, but like yours gave us something more to discuss. But I can tell you that there is another way of doing these things, and this way actually is easier. For example, if I had to implement x plus z, let's say, doing a block encoding of x plus z and then simulating stuff would actually be quite expensive, because x and z are just like very one qubit gates, right? Again, you have to block encode them, take care of the error and ancilla and do stuff. Can we do it in a simpler way? S- Think about this. So let's say all of your solutions are valid, by the way. All of these work. It's just that we are looking for more elegant ways to do stuff. I'm rubbing this. Yeah, I'll keep that. I'll keep that for the time being. Right? I want it in this particular structure. But obviously, this will give me UV. Now, you take a look at unitary U, right? So, he can apply operators probabilistically, right? So can you think of a way to apply this U plus V operator probabilistically? Without block encodings, is what I'm trying to say. Let's say I want to apply some unitary or some operation on the zero state with probability half. What do I do? Exactly, Hadamard. That's the first step. And I already said that whenever I have a unitary, I'll assume that I have access to the controlled unitary as well, right? So take a look at this circuit and try to analyze this on your own. उतना जरूरत नहीं है. So take a look at this where this is the controlled U operator, which is exactly saying that one tensor one पे मैं U apply कर रहा हूँ, and the control bar V, which is this blank symbol, is 0 tensor 0 पे I'm applying V. Try to analyze this circuit. Try to analyze this circuit and see what output state you have. Take 2 minutes and do the exercise on your own. Try to apply this circuit. You guys have already seen Deutsch Josa, right? So the calculation will involve a step that is very close to the phase kickback step. Phase kickback, when we do this, we expand it and then we rearrange the terms and then we condense it again, right? This calculation also uses something similar to the phase kickback step, not with half probability. You are very close. It's not with half probability. It's, I don't want the amplitude. I'm just saying that any p. Try to do like you work it out, you will get the probability. Oh, sorry, my bad. Someone should have pointed out at the moment I said Deutsch Josa, right? There's a Hadamard after that. I always keep forgetting that Hadamard. Without that, like you just have one application. Yeah, I have defined it. So this is the symbol. Yeah. Yeah. So basically you can think of, yeah, you can think of this as applying an X gate and then doing a controlled operation. So it's the same thing. By the way, I have a question for everybody. Don't you find it weird that if I have, let's say, if I have things of this form, I can write this as alpha phi chi phi. Have you ever thought about this? So let's say I have a phase on this subspace of the Hilbert space, right? I can write it in this form, and in fact, it also acts like the phase is on this subspace instead of that. Huh? Yeah, it's a global phase. I mean, it does not need to be a global phase, right? If there is some other thing, I can still bring it out in front, right? It can be a relative phase also. Has anyone even wondered about this, like when you were learning about quantum stuff? Yeah, yeah. I mean, for the physicists, like these are like just meals at the end of the day. But for the rest of us, like who have not dealt with these Hilbert space objects, I have a long-term assignment for you and bothered the quantum information guys with it. Ask them how that actually works. That you have a phase on some subspace, because this is a very critical thing in Deutsch Josa, right? You have the phase somewhere, suddenly the phase comes in front of something else. Mathematically, it's fine because you are just doing a tensor and you're taking the product out. What is the physical interpretation of this? So this is a long-term assignment for the quantum information people. But yeah, like because all of these concepts sort of use that we use this thing over and over implicitly, right? And this is also one of the things that tends to this church of the larger Hilbert space. So Just tying everything, like all the loose ends at once. Let's analyze this now. You have had enough time. Yeah, yeah, yeah. Okay. So we are applying a Hadamard. We are going for square root 2 of 0 Hadamard, control U and control not V, right? So we have 0 tensor UV, sorry, U psi plus 1, no, this is V, right? 0 tensor V, huh? And 1 tensor U psi, right? Okay. Now we are applying another Hadamard. So we get half out in front. 0 plus 1 हो जाएगा ये. So this will be 0 V psi plus 1 V psi plus 0 U psi, because this will become 0 minus 1 now, minus 1 V psi, right? Sorry, U psi. Half 0 common, U plus V psi minus 1 V minus U. Sorry, plus V minus U psi, right? So therefore we see that probability 1/4, with probability 1/4, we have applied U plus V to psi. If we measure 0 in the first register, and we have also applied V minus U, so would you agree that this is a much simpler method than just doing the block encoding of V and U and then applying it? There is no error involved over here. And there is no construction of the larger unitary, right? Because in the block encoding, you actually have to construct the larger unitary. There is no construction. I can just directly apply and do this. Probability will there be in block encoding as well, right? Because V minus U might be no like super one, right? The spectral number V plus U. So you will have a normalization factor there also. Everything is probability. Like probability is not one in any case. And there's a huge thing that I'm skipping over in this session is how do I go from that root P to something close to one? Because again, okay, just a small digression from what we are doing so far. We can't do amplitude amplification on that step. Can someone tell me why? So the root P U psi, we can't do an amplitude amplification on that. You don't know psi. Very good. You don't know what psi is, right? This is the same problem we ran into the HHL part, right? If I don't know what the state is, I can't apply amplitude amplification. So I need something given to me explicitly. Fortunately, as it turns out, there is a one of the HHL improvement papers by Child, Kothari, and again I forget who the third person was, ac- actually introduced this thing called oblivious amplitude amplification. Amplitude amplification. Take my word for it that you can actually amplify that using techniques which are very similar to amplitude amplification. The only problem is now instead of 1 over root p, so if the amplitude of that state is at like the probability of the state is p, now instead of 1 over root p, I have to pay a little bit more. So when you guys go to quantum complexity, which is I think much later on down the road, there is a sort of algorithm which is this quantum Merlin Arthur algorithms. They'll like talk about this error reduction algorithms, right? I think like Professor Devojyoti already talked about this concept of error reduction, right? It is much more general than what you have seen, this concept of error reduction. In fact, for randomized algorithm, you have completeness and soundness, you want to like preserve that gap, right? So similar kind of ideas actually come into play for this oblivious amplitude amplification. This is a very non-trivial amplification algorithm. It has very little to do with like the structure looks like Grover's, but the analysis is completely different. I just don't want you to go home and think, okay, he said that psi is not given. How are we even amplifying this state? There is a way to do this, which we will not be covering today. But Coming back to the task at hand, we see that this easy circuit given to us allows us to implement this U plus V architecture. Now immediately you can see, if I have two block encoded matrices, we can do this LCU. So this is called an LCU, a linear combination of unitaries. The first extension, we are applying U and V with equal weight. If you consider that the weight on U is 1, the weight on U is V is also 1, right? How do I generalize this? Yeah. How do I generalize this? So let's say if I want some alpha U weight on U and some alpha V weight on V. Sorry, my bad. Very good. Did everyone get this? So instead of Hadamard, now we go for some carefully crafted rotations. So Ry theta and Ry dagger theta. Take this as another homework if you're trying to like read these lectures like up by yourself. Try to see what the weights you get with U and V are, and try to see if they're general enough. This is the first extension. But we see, let's assume for the time being that this rotation is general enough, right? The second extension is, what if we have a collection of alpha j's and uj's? What can we do then? So instead of u and v, now I'm telling you that there is a collection of such alpha, like such unitaries with respective probabilities associated with them. I mean, like you're getting all the solutions. Yes, very good. So has this concept been discussed with you that the Hadamard transform is nothing but like a Fourier transform for one qubit basis, right? Now, what does the Fourier transform actually do? I mean, it has a lot of other applications, but in our case, for the sake of quantum computing, the Fourier transformation is just a change of basis, going from the standard computation basis to some different basis. Again, like if I had time for quantum learning, I would have discussed like why this basis is important. But Fourier basis has a lot of nice properties. Like for example, the Fourier coefficients have a special meaning. The bases themselves are orthonormal to each other. The There can only be a unique Fourier expansion of a particular state. Like these nice properties are there. So what we will do is, we see this structure, right? Now, if I have ui through to uj, automatically I would want something that implements. Everyone agrees? In fact, this makes the algorithm very trivial to see, right? If I have access to the controlled unitary UI, then I can start applying these. There's one more thing that's needed. What's that? So just having access to this won't help. What else is needed? I need a way to encode the weights on the operators also. So for example, here we knew how to encode the weights by using some rotation, right? If I have a generalized structure, it's not very easy to see how to encode the weights. This brings us back to things that look like this. We saw this early in the morning, right? We are just encoding something, right? So if I had an operator, let's say a map that mapped 0 to summation of j alpha j j. Let's keep it at I because we are using I everywhere. If I had a way to do this, combining these two, it should be intuitive by now that we can also get a operator of that form, right? And in fact, it is exactly, I mean, it's not exactly the same as this, but it looks exactly the same as this. So in the literature, you will see that this is something called the prep operator. And this is known as the select operator. So, oh, by the way, everyone knows what this means, right? Like instead of one qubit, I am assuming many qubits. I'm assuming that the state is normalized. Like this is by summation of alpha I squared, something like this. This I'm assuming that the state is normalized. You can just think that alpha is at just amplitudes and they add up to one. I can't bother with the normalization right now. This, try running this on your own copies and seeing if it actually implements summation of alpha I ui I. Try doing this. There is one small step involved. For example, the prep and the select are pretty straightforward. You sort of get that's the step that's involved. You immediately get sort of a summation of I. So you start with I shy. Start with this. Then because of I'm applying the UI operator on this. So I get UI shy. The prep dagger is basically nothing but summation of alpha k. When I multiply these two things, you can just take the Kronecker delta, right? Whenever k equal to j, I have square. Whenever k not equal to j, that state does not exist. Inner product is 0. So I get out alpha ui psi. And there is the I state also. But yeah, fine. Now, can anyone look at the HHL algorithm that we did in the morning and try combining block encoding and this and try seeing what parts can be expressed in these forms? The prep state is exactly what TB did, right? And the select state is exactly what what the conditional Hamiltonian was on the clock operator, right? So not only did we see a way of interpreting HHL as a block encoding, now we are seeing a way of interpreting HHL as a linear combination of unitaries. This should like start making sense, right? So I just showed you two frameworks. I have till 1:30, right? Oh, sorry. Okay. I'll try to wrap up fast. So we saw two frameworks which can extend the thing that we have already seen. I'll end with one more like a short version of what this thing called block Hamiltonian simulation does. So that there we will start tying in everything together. I think I should do it after the break. Like I have a half an hour more because it will take. Okay, so let's break here. Go out armed with this knowledge. Think about it. We'll come back and tie all the loose steps up. So we now, because we know what block. Okay, sorry. We know what block encoding is, and we know what linear combination of unitaries does. The last step would be try to combine these two things. Once we combine these two things, we are well on our way to qubitization. There, I'll let Sham take over with quantum walks. But yeah, let's break here for now. Like any questions you can ask me like after the break. I'm sure you all are famished. I'm extremely sorry about overshooting.